For most of modern astronomy, humanity has lived inside a colossal misunderstanding. For 70 years, textbooks, documentaries, and scientific charts described our home galaxy, the Milky Way, as 100,000 light-years wide. That number appeared in every classroom, etched into the minds of students and professors alike. It was treated as a fact as solid as gravity itself, until new evidence revealed that we had been living inside a cosmic illusion. The Milky Way, it turns out, is not merely large. It is at least twice that size, possibly even greater. Our galactic home stretches across a domain so vast that every map we have drawn for generations has been only a rough sketch of a much larger reality. The implications ripple through every branch of astronomy. If our galaxy is twice as wide, then its total volume, its mass, its gravitational pull, its collection of stars and planets is far greater than we ever imagined. This discovery doesn't simply add a new line to a textbook. It forces science to rebuild its foundation, to question how we measure the universe, how galaxies evolve, and even how close we truly are to our neighbouring giant Andromeda. The realization began quietly, with subtle clues that something about our numbers didn't make sense. Astronomers had noticed inconsistencies for decades. Stars at the galaxy's edges were moving faster than they should. Satellite galaxies orbited farther out than the known gravitational field could explain. The mass we could see never balanced with the mass implied by motion. Each puzzle piece hinted that our map was too small, yet the data were fragmentary, incomplete, just whispers of something enormous hiding beyond sight. Then technology changed everything. New instruments like the Gaia spacecraft, radio arrays tracing hydrogen gas, and the James Webb Space Telescope began to expose the Milky Way's true shape. Each mission peeled back another layer of darkness, revealing structures far beyond the boundaries scientists once drew with confidence. Slowly, the evidence converged into a single staggering truth. The Milky Way extends far past the bright disk visible in optical light, expanding into a diffuse halo of stars, gas, and dark matter that doubles its known diameter. The mistake wasn't due to negligence or arrogance, it was the inevitable result of perspective. We have been trying to map a structure from within it, like an ant attempting to chart the entire forest while standing on one leaf. From our position, 26,000 light-years from the centre, we see only a narrow window of the galaxy, our view blocked by clouds of dust and gas that swallow starlight. We cannot step outside for perspective, so every measurement is a reconstruction based on partial clues. For decades, astronomers estimated the Milky Way's extent by counting bright stars and noting where their density thinned into darkness. That limit where the visible light seemed to fade became the supposed edge of the galaxy. It was a reasonable assumption, but deeply flawed. The Milky Way doesn't end abruptly like the rim of a coin. It tapers, fading gradually into space. Stars extend in long, faint streams. Invisible matter stretches even farther. The boundaries we drew were simply where our instruments gave up, not where the galaxy truly stopped. As technology improved, those limits shifted outward again and again, each generation of telescopes expanding our known frontier. But the latest measurements didn't just push the line, they shattered it. The new Milky Way is a different creature altogether, a sprawling titan of stars and invisible mass, twice as wide and several times heavier than once believed. The consequences reach far beyond the numbers themselves. A larger galaxy means a stronger gravitational influence, which alters predictions about our eventual merger with Andromeda. It affects how we model dark matter distribution and how we interpret the motions of surrounding galaxies. It changes the number of stars that could host planetary systems, and thus the potential for life. More stars mean more worlds, more possibilities, more unknowns. The discovery also carries a humbling message. If we misjudge the very galaxy we inhabit, what does that say about our understanding of the universe beyond? Every galaxy we've measured from afar was mapped using the same assumptions that led us astray here. Perhaps every cosmic atlas we've drawn underestimates reality by the same margin. The universe may be far larger, denser, and more connected than our equations suggest. Standing beneath the night sky, it's easy to think we see the Milky Way, a shining river of stars stretching across the heavens. But what we see is only its luminous skeleton, a fraction of its true body. 90% of the galaxy is invisible to the human eye, hidden in wavelengths our senses cannot perceive. we have been staring at the tip of a cosmic iceberg, mistaking its surface for the whole. The revelation is not merely scientific, it is existential. It reminds us how small our knowledge still is, how easily we mistake the limits of perception for the limits of truth. The Milky Way was never what we thought. It is larger, older, more intricate. A sprawling, luminous mystery wrapping around us in every direction. And after 70 years of confident error, we are finally beginning to see our home for what it truly is. Not a modest spiral in a quiet corner of space, but a galactic giant we barely comprehend. Trying to measure the Milky Way is like trying to describe the shape of a vast glowing ocean while drifting inside its depths with no way to surface for perspective. From our position within the galactic disk, every direction we look is tangled with billions of stars drifting dust and colossal clouds of gas that scatter and absorb light. We live in the middle of the thing we're trying to chart, trapped by its brilliance and its opacity. For most of human history, that limitation shaped every misconception we held about our galaxy. We could not see its true form, only scattered fragments that peeked through windows in the dust. Even today, our instruments fight against that blindness. The Milky Way's central bulge, where the greatest concentration of stars lies, is wrapped in dense curtains of interstellar soot that hide it from visible light. To pierce those veils, astronomers must rely on infrared telescopes, radio surveys, and space observatories that orbit above Earth's distorting atmosphere. Yet even with all this technology, mapping the Milky Way remains one of science's most delicate acts of inference. An enormous three-dimensional puzzle, pieced together from motions, shadows, and echoes of light. Early astronomers, armed only with optical telescopes, faced an impossible task. They counted stars and plotted their brightness, hoping to estimate the galaxy's shape by where those stars seemed to cluster most densely. What they drew was a flat disk, with the sun roughly near the centre, an understandable but entirely wrong conclusion. Only when radio astronomy developed after World War II did scientists begin to see through the dust. By tracing emissions from neutral hydrogen, which radiates at a wavelength of 21 centimetres, they could map the structure of our spiral arms for the first time. But even those early radio maps were crude, distorted by assumptions about distance and motion. To gauge how far away an object lies, astronomers depend on indirect techniques, measuring parallax shifts as Earth orbits the Sun, estimating brightness compared to known luminosity, or deducing distance from Doppler shifts in spectral lines. Each method carries uncertainties, and when those uncertainties multiply across thousands of stars, small errors balloon into vast distortions. The result was a galaxy half its true size, flattened and simplified to fit the limits of our measurements. We were looking through a keyhole and mistaking the narrow patch of light for the full horizon. One of the deepest challenges in measuring from within is that the Milky Way's rotation complicates everything. The galaxy spins, but not like a rigid wheel. Stars closer to the centre orbit faster, while those on the outskirts lag behind, creating a swirl of differential motion. Because we are ourselves part of that motion, our entire frame of reference is moving. Imagine trying to chart the flow of a river while being carried along by its current. You can only infer its shape by the speed of the water around you. This is how astronomers study our galaxy, by tracing how gas clouds and stars move relative to the Sun, calculating invisible orbits from shifting wavelengths. Each small clue builds toward a larger portrait, but that portrait is never final. The moment one piece is clarified, another dissolves into uncertainty. For much of the 20th century, scientists believed the Milky Way was bordered by emptiness, that beyond its visible disk lay the dark silence of intergalactic space. Yet as instruments grew more sensitive, faint signatures began to appear where none were expected. Stray stars, tidal streams, and diffuse halos of gas extending far beyond the supposed edge. These discoveries suggested that our galaxy doesn't end abruptly, but fades gradually into the surrounding cosmic medium. The farther we looked, the more it expanded, as though the galaxy itself were breathing outward into infinity. Measuring from within means confronting constant illusions. Dust clouds can mimic empty space. Overlapping star clusters can seem like distant galaxies. Gravitational lensing can bend light in ways that distort true positions. Every correction reveals a deeper layer of complexity. Even today, with the European Space Agency's Gaia mission mapping the positions of more than 1 billion stars with micro-arc-second precision, we still face uncertainties about the Milky Way's total extent. Gaia gives us exquisite detail within a few tens of thousands of light-years, but beyond that, distances blur into probability. Our understanding of the galaxy's structure depends on modelling rather than direct observation. We infer spiral arms, warps, and thickness from patterns of stellar motion, not from a direct bird's-eye view. We have never truly seen the Milky Way as an object, only as a phenomenon surrounding us. If we could somehow escape it and look back from millions of light-years away, we might find that our mental picture, those tidy artist renderings of a symmetrical spiral with neat arms and a bright nucleus, bears little resemblance to the messy, sprawling truth. Our galaxy is warped, asymmetrical, scarred by past collisions and fringed with streams of stars torn from smaller systems. The picture is not a painting of order, but a story of motion and change. To measure it from within is to accept uncertainty as permanent. We refine our tools, we sharpen our equations, but the horizon always shifts. The Milky Way reveals itself in fragments, each discovery both answering and deepening the mystery. And perhaps that is fitting. Living inside a galaxy means that its boundaries will forever recede before us, like the horizon of an endless sea. The first real cracks in the old model of the Milky Way appeared not through light but through motion. Astronomers began to notice faint trails of stars that stretched across the sky like ghostly fingerprints. Stellar streams arcing through the galaxy's outskirts, forming pale ribbons barely distinguishable from the background. These weren't random alignments. They were remnants of ancient collisions, fossil traces of smaller galaxies torn apart by the Milky Way's gravity. Each stream told a story of cosmic cannibalism, of star systems devoured and scattered into orbiting debris. For decades, such structures went unnoticed, hidden within the dense star fields that encircle our night sky. Only with precise surveys and advanced algorithms did their patterns emerge, revealing that the outer Milky Way was not empty, but alive with movement and memory. Each discovery stretched the known boundaries of our galaxy further, suggesting that what we once thought of as its edge was instead just the beginning of a vast halo of stellar remnants. These streams became keys to understanding the true scale and mass of the Milky Way. By tracing their orbits, astronomers could map the invisible gravitational landscape that guided their paths. The stars in these streams move like leaves in an invisible wind, their trajectories curving in response to the galaxy's unseen weight. From those subtle deflections, scientists could infer the presence and distribution of dark matter, the mysterious substance that forms the bulk of our galaxy's mass. It was through studying what we could not see directly that we began to perceive the immense shadow surrounding us. The halo of dark matter extends far beyond the luminous disk, perhaps 1 million light-years in diameter, forming a ghostly architecture that shapes everything we observe. Within this shadowy realm, countless stellar streams weave and twist, each one a thread in the Milky Way's tapestry of formation. The discovery of these structures reshaped our understanding of galactic growth. The Milky Way was not born whole. It was assembled piece by piece through the steady accretion of smaller systems. Every dwarf galaxy that strayed too close was stretched and shredded, its stars flung into looping orbits that still encircle us today. Some of these streams, like the Sagittarius stream, the most famous of them all, wrap around the galaxy multiple times, a luminous scar marking the site of an ancient feast. To map them is to reconstruct the history of cosmic hunger, to read the record of every merger that built our home. But the streams also revealed something else. The gravitational field that shapes them is not smooth. Their paths wobble, twist, and kink, as if tugged by invisible hands. Those distortions are signatures of dark matter, clumps, small, dense concentrations scattered throughout the halo like stones beneath a river's surface. Each one bends the motion of stars that pass nearby, leaving a subtle ripple in their trajectory. By studying these ripples, scientists can infer the texture of dark matter itself, testing competing theories about its nature. Some models suggest it forms diffuse clouds, others predict it exists in compact subhalos the size of star clusters. The streams act as cosmic seismographs, recording every tremor in the gravitational field, even the spaces between them, those regions where stars seem sparse and light fades into nothing speak of structure. The darkness is not emptiness, but a medium of unseen matter, influencing the flow of everything within it. It is through these shadows that we glimpse the skeleton of the Milky Way. The halo defines the galaxy's reach far more than its luminous disk does. What we perceive as the Milky Way's body, the spiral arms and the glowing centre, is merely its core, the visible part of a much larger organism that stretches far beyond the night sky's glow. The streams trace the outline of that hidden structure, showing us where the galaxy's gravitational influence fades into intergalactic space. As astronomers followed these stellar trails deeper into the darkness, they realised that the Milky Way's borders could no longer be defined by light alone. The galaxy's influence extends as far as its gravity can reach, encompassing regions once thought to belong to empty space. And as new surveys revealed ever more faint and distant streams, the line separating the Milky Way from the cosmos around it grew increasingly blurred. The streams also raised a deeper philosophical question. If the Milky Way is constantly consuming and merging with other systems, where does it truly end and the next galaxy begin? Each stream is both an ending and a beginning, the remnants of one world and the building blocks of another. We are part of that continuum, living inside a galaxy still in the act of becoming. What we once saw as a static structure is now understood as a dynamic process, an endless cycle of creation and destruction. Through these streams and shadows, we have learned that the Milky Way is not a finished thing but a living system, sculpted by gravity's long patience. Every faint arc of stars, every hidden trail across the darkness is a memory of motion, a whisper from the past echoing through the present, telling us that our galaxy is far vaster, older, and more complex than we ever imagined. The more astronomers studied the movement of stars and gas in the Milky Way, the clearer it became that something unseen was exerting an enormous influence. The stars on the outskirts of the galaxy, far from the bright central bulge, moved far faster than gravity from visible matter could explain. According to Newtonian physics, objects that far from the centre should drift lazily, orbiting slowly around the galactic core. Instead, they sped along as if an invisible hand were pulling them. This discrepancy wasn't unique to our galaxy. It appeared in every large spiral system ever studied. The missing force hinted at a vast quantity of matter that emitted no light, absorbed no radiation, and revealed itself only through gravity. Astronomers named it dark matter, not because it was dark in colour, but because it was entirely invisible, its nature hidden from every telescope. What began as a curious anomaly evolved into one of the greatest revelations of modern science. Most of the Milky Way isn't made of stars, planets, or glowing nebulae. It is built upon a colossal, unseen foundation, a halo of dark matter encompassing the galaxy like a ghostly cocoon. This halo extends well beyond the visible disk, forming a gravitational sphere so immense that the Milky Way's familiar spiral is merely its luminous core. Every star, every orbit, every stream of gas moves within that hidden architecture. Without it, our galaxy would fly apart. The luminous matter, the shining part we see in photographs, accounts for less than 10% of the total mass. The rest is a vast ocean of invisible substance shaping the Milky Way from the shadows. The existence of the halo reshaped how scientists think about galaxies. Instead of isolated islands of starlight, they are now understood as structures wrapped in massive envelopes of dark matter. The visible component stars, gas, dust form at the centres of these halos, condensing like dew within a cosmic fog. Over billions of years, these halos collide and merge, their gravity sculpting the large-scale structure of the universe itself. Every cluster, filament and void in the cosmic web traces the distribution of this mysterious material. The Milky Way's halo is a microcosm of that universal framework. Though we cannot see it directly, its presence is mapped through its effects. When astronomers track the orbits of distant globular clusters and satellite galaxies, they find that those objects move too swiftly to be bound by visible mass alone. The only explanation is that an immense diffuse cloud of dark matter surrounds the galaxy, its gravity holding everything in place. In some regions, this halo may contain dense substructures, clumps of concentrated dark matter left over from the galaxy's formation. These clumps subtly disturb the orbits of stars and streams, leaving measurable imprints. By studying these distortions, scientists can infer the halo's shape and density, much like a sculptor feeling the contours of a hidden statue beneath a cloth. Yet the exact nature of dark matter remains elusive. Is it made of exotic particles that barely interact with normal matter? Or is it an illusion, a sign that our understanding of gravity itself needs revision? Experiments deep underground and in orbit search for faint interactions, but so far the evidence remains indirect. We know the halo exists because without it, the Milky Way's outer stars would escape into space. Its invisible gravity keeps them tethered, like unseen threads binding a cosmic wheel. The concept of the galactic halo challenges human intuition. We are accustomed to equating reality with what can be seen, yet the majority of our galaxy's mass lies hidden beyond the reach of light. If we could visualize it, the halo would appear as an enormous sphere dwarfing the bright disk, glowing faintly with potential energy. The Sun, which orbits about halfway out from the center, would appear not near the galaxy's edge but buried deep within its invisible body. In truth, we live inside a gravitational ocean, immersed in a sea of unseen mass that extends far beyond the most distant stars we can detect. The realization that most of the universe's matter is invisible was both humbling and revolutionary. It revealed that our senses and even our best instruments grasp only a sliver of reality. For every shining star we see, there exists an order of magnitude more matter cloaked in shadow. The galactic halo, therefore, is not an afterthought but the main stage upon which the drama of the Milky Way unfolds. Its gravity dictates how gas condenses, how stars form, how spiral arms rotate, and how satellite galaxies dance around the central mass. Even the fate of the Milky Way's future collision with Andromeda depends on the invisible halos that surround both galaxies. When they finally meet, it will be the halos, not the stars, that first intertwine dark colliding with dark, long before the visible disks ever touch. Through this lens, we begin to understand that the Milky Way's true form is not what gleams across the night sky, but what lies unseen beneath it. The galaxy's brilliance is merely the glowing tip of a vast hidden empire of mass, structure, and mystery that defines the universe itself. As the Milky Way's hidden mass came into focus, another revelation began to unfold, the discovery that our galaxy rules over a vast entourage of smaller companions, each one bound by its gravity and moving in slow, graceful orbits through the darkness. For a long time, astronomers believed only a handful of these satellite galaxies existed. The large and small Magellanic Clouds visible from the southern hemisphere, and perhaps a few faint smudges scattered across the sky. But deeper surveys revealed dozens more, and now we suspect there may be hundreds. They range from dim, irregular clouds of ancient stars to nearly invisible dwarf spheroidals, whose light is so faint it barely reaches us. These companions are more than mere curiosities. They are the keys to understanding the Milky Way's reach and power. Each one moves within the galaxy's gravitational field, tracing invisible paths that reveal how far that field extends. The orbits of these dwarfs, some stretching hundreds of thousands of light-years from the galactic center, mark the true boundary of the Milky Way's dominion. They show us that the galaxy's influence reaches far beyond its bright spiral arms into regions where almost no visible matter exists. To contain so many satellites, the Milky Way must possess enormous mass, far greater than can be accounted for by its stars alone. That realization further confirmed the existence of the galactic halo, an unseen sphere whose gravity commands not only the stars of the disk, but entire galaxies drifting in its orbit. The Magellanic Clouds, our most prominent satellites, are vast systems in their own right, each containing billions of stars, and they are currently being drawn inexorably inward, their gas streams forming a long, ghostly arc known as the Magellanic Stream. This colossal ribbon of hydrogen extends across half the night sky, a tidal bridge connecting the clouds to the Milky Way, evidence of the gravitational dance that will eventually end in their absorption. Through these interactions, we witness galactic evolution in real time. The Milky Way is not a static entity. It is a predator and creator, constantly consuming and reshaping smaller systems. Many of the faintest dwarfs discovered in recent years are little more than remnants of galaxies already torn apart, their stars stretched into thin streams that wrap around the halo like strands of silk. These systems record the Milky Way's ongoing growth, each one a fossilized moment in its long history of expansion. As our telescopes and algorithms grow more sensitive, we continue to find even smaller companions, tiny galaxies that challenge our definitions of what a galaxy is. Some are only a few hundred light years across, with fewer stars than a single large star cluster, yet they orbit the Milky Way as sovereign systems, held together by their own dark matter halos. Their existence provides critical clues to the nature of dark matter itself, suggesting that it clumps into structures at every scale. The distribution of these satellites, however, poses new mysteries. Many of them appear to orbit along a common plane, forming a vast ring-like structure rather than a random scatter. This unexpected alignment has sparked debate about whether the dwarfs formed within the Milky Way's halo or were captured as part of a larger system that fell in long ago. If they were once bound to a single ancient parent galaxy, their current arrangement could be the ghost of that lost structure, a memory written in orbital geometry. Each discovery deepens our understanding but also complicates the story. The further we look, the more the galaxy expands, not in size but in scope. What we thought of as a single entity, the Milky Way, is, in truth, an ecosystem. Its satellites, streams and halo form a continuous gravitational web, a dynamic structure that blurs the line between one galaxy and the next. Even the region we call intergalactic space is not truly empty. It is threaded with faint bridges of dark matter and gas that link the Milky Way to its nearest neighbours. Our galaxy's reach extends so far that the boundary between its halo and that of Andromeda may already overlap. In that sense, the two systems are not separate islands at all, but parts of a single gravitational archipelago slowly converging into one. Measuring that reach has been one of astronomy's greatest challenges. The velocities of satellite galaxies provide a natural test. If they move faster than the Milky Way's gravity can contain, they should drift away into the void. But instead, even the most distant dwarfs remain bound, their orbits stable and slow. This means the Milky Way's mass must be immense, perhaps 4 trillion times the mass of the Sun. The halo's edge, if it can be called that, may stretch nearly 1 million light-years from the centre. Within that invisible sphere, the galaxy reigns supreme, pulling on everything inside its grasp. The satellites remind us that the Milky Way is not a solitary wanderer, but the heart of a vast cosmic system, a gravitational empire whose rule extends far beyond the reach of light. Each faint, flickering companion is both a survivor and a sacrifice, a fragment of cosmic history moving in endless procession around its great master. Together they trace the unseen contours of the galaxy's power, revealing that even in the silent darkness beyond the last visible stars, the Milky Way's influence endures, shaping the fabric of space itself. Trying to comprehend the true scale of the Milky Way is like attempting to imagine infinity confined within a single thought. Numbers lose their meaning, language falters. Astronomers tell us that our galaxy spans around 200,000 light-years across, twice the size once believed, and that statement alone collapses under its own enormity. A single light-year measures nearly 6 trillion miles. To cross the Milky Way from one side to the other, travelling at the speed of light, would take 200 millennia longer than Homo sapiens have existed as a species. Every beam of starlight we see from the galactic rim began its journey when Earth was locked in the last ice age, when glaciers still covered much of the northern hemisphere. We live in a structure so vast that time itself becomes part of its geometry. To grasp such distances, we must abandon ordinary measures and think in cosmic scales. Our Sun orbits the centre of the galaxy at a distance of about 26,000 light-years, moving at nearly 500,000 miles per hour. Even at that incredible velocity, it takes more than 200 million years to complete a single orbit. In all of human history, we haven't moved through even a fraction of 1% of that path. The last time the Sun was in its current position relative to the galactic centre, the dinosaurs still ruled the Earth. When we look up at the Milky Way as a faint milky band crossing the night sky, we're glimpsing the cross-section of this vast rotating system from within a glowing slice of the spiral disk filled with billions of suns. That band represents only the innermost layer of the galaxy. Beyond it lie faint outer arms, clouds of hydrogen gas, and the immense dark halo that swaddles everything. The visible galaxy is like the shining core of a lantern whose outer glass has gone invisible. Its true structure, if we could view it from afar, would be a sprawling, warped spiral, its arms twisted and asymmetrical, its edges feathered with stray stars. Yet even this immense structure is just one among hundreds of billions. The scale of the Milky Way only acquires its full meaning when placed in context with the rest of the universe. Our nearest major neighbour, the Andromeda Galaxy, lies roughly 2.5 million light-years away, a number that, by galactic standards, is surprisingly small. Between the two stretches a tenuous bridge of gas and dark matter, a faint gravitational thread linking them together. Beyond that, countless other galaxies form clusters and filaments that weave the vast cosmic web. Within this web, the Milky Way is merely a bright node, a single luminous whirlpool in a sea of others. The mind rebels against such immensity. To visualize the galaxy, astronomers often resort to metaphors. If the solar system were the size of a coffee cup, the Milky Way would be the size of North America. If the sun were a grain of sand, the galaxy would stretch wider than the Earth itself. These comparisons help for a moment, but they fail to capture the overwhelming truth that within our galaxy alone, there are more stars than grains of sand on all the beaches of Earth. Each one may host planets, moons, and perhaps life. Our entire history, every civilization and dream, unfolds on a single speck orbiting one of those countless stars, lost in an ocean so vast that our species has not yet seen beyond its shallows. Yet this awareness, rather than diminishing us, connects us to something larger. When we gaze at the Milky Way, we are not looking outward but inward, into the structure that cradles our existence. Every photon that reaches our eyes has travelled through that immense spinning system, carrying the story of where we come from. The galaxy is not merely a backdrop for life, it is the environment in which life arose, the vast cosmic womb that made our atoms and gave them motion. The scale of the Milky Way reminds us of the unity of all things. The same processes that form stars in distant arms also created the elements in our bodies. The light of supernovae long dead glimmers in our blood and bones. When we measure the galaxy, we are, in a sense, measuring ourselves. The size of the Milky Way is not a number to memorize, but a revelation to absorb, a testament to the depth and mystery of existence. To comprehend it is to feel both infinitesimally small and profoundly connected, to realize that within this immense spiral of light and shadow, we are not spectators but participants in an ongoing cosmic story. The scale humbles us, but it also elevates us. For in recognizing our tiny place in this grand design, we also recognize that the universe, in its vastness, has given us the capacity to understand it. The galaxy's immensity is not meant to isolate us, but to remind us that even in a universe measured in trillions of miles, consciousness has found a way to look back and call it home. For all its quiet beauty, the Milky Way is not drifting through the universe in peace. Every star, planet, and cloud of gas within it is moving along a slow and inevitable path toward a grand cosmic event, a collision with our nearest spiral neighbour, the Andromeda Galaxy. Astronomers have long known that both galaxies are approaching each other, drawn together by their mutual gravity, but recent measurements have made the picture clearer and more dramatic. Using data from the Hubble Space Telescope and the Gaia mission, scientists have calculated that Andromeda is racing toward us at roughly 110 kilometers per second. In 4 billion years, give or take a few hundred million, the two colossal systems will meet head-on. The thought of galaxies colliding sounds cataclysmic, as though stars will smash into one another and worlds will burn. But the truth is stranger and more elegant. Galaxies are mostly empty space. The vast distances between stars mean that direct collisions are rare. Instead, when the Milky Way and Andromeda meet, they will pass through each other like ghosts, their shapes distorted by gravity, their stars flung into enormous tidal tails that sweep across space. The collision will be an event of gravity, not impact, a slow, swirling ballet lasting billions of years. Yet the consequences will be profound. Both galaxies will lose their distinct spiral forms as their stars mix and their gas clouds ignite in bursts of star formation. In time, they will merge completely, forming a single massive elliptical galaxy often called Milkomeda. For a brief span of cosmic time, the night sky from any surviving planet will be spectacular beyond imagination. As Andromeda grows larger in our sky, its spiral arms will stretch from horizon to horizon, glowing with billions of suns. During the final approach, the combined light of both galaxies will turn the heavens into a continuous river of fire. Though this distant future lies beyond the lifespan of our Sun, the idea captures something deeply human. The recognition that even cosmic structures are impermanent, destined to merge, evolve, and transform. The merger between the Milky Way and Andromeda is not an isolated event. It is part of a larger dance within the local group, the small cluster of galaxies bound together by gravity. Both giants are already surrounded by retinues of dwarf galaxies, many of which are being drawn inward along converging orbits. In the long run, every member of this group will coalesce into one vast galactic remnant. Our galaxy's doubled size and increased mass mean that the gravitational encounter will be even more dramatic than once believed. Early models, based on the assumption of a smaller Milky Way, predicted a gentler interaction with minimal displacement of stars like the Sun. But new simulations suggest otherwise. With both galaxies now understood to be roughly equal in size and mass, their mutual pull will be stronger and their merger more complete. The Sun itself, carried along by the Milky Way's motion, may be flung into a new orbit hundreds of thousands of light years from its current position. It could end up in a distant halo circling the merged galaxy's core, or even be ejected into intergalactic space altogether. Still, for a time, our descendants, if they exist, would see Andromeda approach like a rising tide of light, a cosmic premonition of transformation. The collision will also reshape our understanding of galactic evolution. We often think of galaxies as long-lived, stable structures, but they are dynamic entities, constantly colliding, merging, and changing. The universe itself builds complexity through these encounters. The Milky Way was once much smaller, assembled through the absorption of countless dwarfs over billions of years. The coming collision with Andromeda is simply the next chapter in that story, a larger-scale continuation of a process as old as the universe itself. Even the timing of this event has philosophical implications. By the time it happens, the Sun will have exhausted its hydrogen fuel and begun its slow transformation into a red giant. Life on Earth will be long gone. Yet in that far future, the stars of both galaxies will continue to burn, merging into new generations of light that will shine long after the last trace of humanity fades. The collision reminds us that creation and destruction are not opposites in the cosmos, they are partners. Every merger gives rise to new forms, new stars, and new possibilities. In the end, what we call the Milky Way will cease to exist, but something grander will take its place. A single, massive galaxy, born from the fusion of two giants, luminous and eternal in its motion. The story of the coming collision is not one of ruin, but of renewal, a reminder that even at the larger scales, the universe remains an artist, sculpting new beauty from the remains of the old. Once astronomers accepted that the Milky Way was far larger than previously imagined, the next question was how massive it truly was. Measuring the weight of a galaxy is not like placing an object on a scale. It requires interpreting the motion of stars, gas, and even entire satellite galaxies to infer the total gravitational pull that binds everything together. The visible matter, the glowing stars, nebulae, and dust accounts for only a small fraction of that mass. What gives the Milky Way its enormous gravitational strength is the invisible empire of dark matter that forms the vast halo surrounding it. By tracking the velocities of distant stars, astronomers discovered that the galaxy must weigh at least 4 trillion times the mass of the Sun, an almost incomprehensible figure. This revelation reshaped not just our understanding of the Milky Way, but also of the cosmos itself, for it suggested that the overwhelming majority of the universe's mass resides in substances we cannot see or touch. Dark matter is the scaffolding of galaxies, the unseen framework upon which the visible universe is built. Without it, the Milky Way's luminous disk would not exist. Its spiral arms would disperse into space, and stars like the Sun could never have formed in stable orbits. The halo of dark matter extends far beyond the edges of the visible galaxy, enveloping it in a gravitational field so vast that even small galaxies hundreds of thousands of light-years away feel its pull. When scientists modelled this distribution, they realised that our galaxy's sphere of influence likely stretches close to 1 million light-years in radius. That means the Milky Way's gravitational domain reaches halfway to Andromeda. Between these two titans, their halos are already touching, creating a shared gravitational frontier that marks the early stages of their eventual merger. This immense weight gives the Milky Way its cosmic authority, a dominion defined not by light but by gravity. Yet, understanding how such mass came to be distributed remains one of astronomy's greatest challenges. Some of it was acquired through collisions and mergers, each event adding the remnants of smaller galaxies to the Milky Way's growing halo. Some of it may have formed in the very earliest moments of the universe, when dark matter clumped together before ordinary matter could cool and condense into stars. Simulations suggest that these halos acted as cosmic molds, guiding the formation of galaxies like ours. Where dark matter gathered, gravity deepened. Where it was sparse, the universe remained empty. The Milky Way's mass, therefore, is not just a number, it is a reflection of the universe's hidden architecture. Every orbit, from the Sun's stable revolution to the erratic paths of far-flung satellites, is governed by this invisible foundation. But even as we refine our measurements, uncertainty remains. Estimates of the Milky Way's total mass vary by nearly a factor of 2, depending on which tracer objects are used. Some researchers suggest that our galaxy could be as light as 1 trillion solar masses, others as heavy as 5. The discrepancy lies in how we model dark matter's density and distribution. If the halo is denser near the centre, the mass estimate decreases. If it is more extended, it increases dramatically. Recent data from Gaia and the Hubble Space Telescope have begun to narrow these uncertainties, suggesting a mass near 4 trillion solar masses enough to make the Milky Way one of the most massive galaxies in the local group, rivaling or exceeding Andromeda. Such a realization shifts our cosmic self-image. For generations, scientists viewed the Milky Way as the junior partner in the coming collision, the smaller galaxy destined to be absorbed. Now it appears that the two are equals, each commanding immense halos of dark matter. Their future merger will not be an act of consumption, but a union between giants. The concept of the Milky Way as a dark matter empire also transforms how we imagine our place within it. We live deep inside that empire, surrounded on all sides by invisible matter. Though we cannot detect it directly, dark matter passes through us constantly, billions of particles streaming through every square centimetre of space. Underground detectors attempt to capture these elusive signals, hoping to identify what dark matter truly is. Some theories propose it consists of weakly interacting massive particles. Others point to axions or entirely new forms of physics. Whatever its nature, dark matter defines the structure of everything we know. The luminous Milky Way, the stars, the nebulae, the swirling spiral arms, is just the visible crown of a far greater kingdom hidden in shadow. In that sense, our galaxy is less a single entity than a manifestation of something vaster, the interplay of light and darkness that has governed the universe since its birth. To weigh the Milky Way is to measure the invisible, and to accept that the brightest parts of reality may also be the smallest. Surrounding the Milky Way like a vast, transparent ocean lies the galactic halo, an invisible realm that stretches far beyond the luminous disk we see in the night sky. It is not a neat boundary, but a diffuse, ethereal expanse where matter grows scarce and gravity still reigns. The halo is composed of two intertwined components, a faint population of ancient stars and globular clusters, and an enormous reservoir of dark matter whose presence can only be inferred through its pull on everything else. Together, they form an envelope so immense that it could easily swallow the visible galaxy a dozen times over. Astronomers once imagined the Milky Way as a flattened spiral with a defined edge, but this outer region defies such simplicity. The halo extends hundreds of thousands of light-years in every direction, possibly approaching 1 million, fading imperceptibly into intergalactic space. It contains relics of the galaxy's youth stars born before the spiral arms even existed, remnants of long-consumed dwarf galaxies, and gas clouds slowly falling inward over cosmic time. Every particle within it moves under the influence of an unseen architecture, a gravitational field woven from dark matter. If we could somehow view the Milky Way from outside, we would see not just a shining disk, but a shimmering sphere of invisible influence stretching far into the cosmic void. This halo acts as both cradle and guardian. It regulates how gas flows into the galactic disk, fueling the formation of new stars, while also serving as a vast repository of material stripped from other systems. Its outermost reaches are populated by hypervelocity stars, rare objects ejected from the inner galaxy by powerful gravitational encounters, some moving fast enough to approach escape velocity, but still bound within the halo's grasp. These travellers mark the outer limit of the Milky Way's dominion, tracing the contours of gravity where light begins to fail. For astronomers, the halo is both a laboratory and a mystery. Its composition and behaviour hold the key to understanding not just the Milky Way's size, but its fate. The halo's mass determines how tightly the galaxy holds its stars, how it interacts with its satellites, and how it will merge with Andromeda in the future. It also offers clues about the early universe. The oldest halo stars, nearly as ancient as the cosmos itself, preserve chemical fingerprints of the first generations of stellar furnaces. Studying them is like reading the fossil record of creation, revealing how the Milky Way grew from primordial gas into a grand spiral. Yet, for all we have learned, the halo remains mostly invisible. It emits little light and hides behind the brightness of the disk. Only through indirect means, such as gravitational lensing, stellar motion mapping, and X-ray observation of hot gas can its outline be traced. Recent observations have revealed that the halo is not uniform. It is lumpy, warped, and dynamic. Streams of gas and stars snake through it, remnants of galaxies long devoured. The halo breathes, exchanging material with intergalactic space, pulling in fresh gas while expelling others through supernova-driven winds. It is not a static shell, but a living system, constantly shifting and evolving. Even the boundary between the Milky Way's halo and Andromeda's may no longer exist as a clear divide. The two vast envelopes likely overlap already, forming a shared region of tenuous gas and dark matter, an invisible bridge binding the galaxies together long before their visible collision begins. Within this realm, the concept of our galaxy becomes less distinct, replaced by a continuum of gravitational influence. For us, living deep within this invisible empire, the halo is both protector and reminder. It shields the galaxy from cosmic radiation, helping preserve the delicate balance that allows stars and planets to form. It also reminds us of our blindness, that most of what holds our universe together is unseen. If our eyes could detect dark matter or the faint glow of the hot gas permeating the halo, the night sky would no longer be a dark canvas sprinkled with stars. It would blaze with diffuse light in all directions, revealing that we are immersed in a structure far vaster than we ever imagined. The galactic halo stands as the ultimate symbol of cosmic humility. It is a monument to everything that escapes perception, a silent confirmation that the universe is not defined by what shines, but by what endures unseen. To explore it is to confront the boundaries of knowledge itself, to acknowledge that our greatest discoveries often lie in the shadows beyond light. The halo is not merely the edge of our galaxy, it is the threshold of the unknown, a vast invisible realm where the Milky Way dissolves into the infinite fabric of the cosmos. When astronomers began mapping the movement of stars throughout the Milky Way, they expected to see a familiar pattern in stars orbiting quickly around the galactic centre, while those farther away moved more slowly, their speed diminishing as distance increased. This pattern, known from the laws of Newtonian dynamics, describes how gravity weakens with distance, yet what they observed defied every prediction. Beyond a certain radius, the stars did not slow down. Instead, their velocities levelled off, forming what became known as the flat rotation curve. This discovery was one of the most startling in modern astronomy, revealing that something unseen was keeping the outer galaxy spinning faster than it should. If only the visible matter, the stars, gas and dust, were present, those far-flung stars would have flown off into intergalactic space long ago. Their persistence implied a hidden mass that extended far beyond the luminous disk, generating a gravitational pull strong enough to hold the system together. Thus, dark matter, once an abstract idea, became an unavoidable reality. The rotation curve became its proof, etched into the motion of stars like an invisible signature. Every galaxy observed since then exhibits the same behaviour, confirming that this phenomenon is not unique to the Milky Way, but a universal feature of the cosmos. The flatness of the curve means that mass does not decline with distance as expected. Rather, it continues to increase, suggesting that galaxies are enveloped by vast halos of unseen matter. For the Milky Way, this revelation helps solidify the concept of the dark halo stretching nearly 1 million light-years across, dominating the galaxy's mass. But even with this understanding, mysteries remain. The precise shape of the rotation curve near the outer edge of the galaxy is still uncertain, because those regions are sparsely populated with observable stars. Astronomers rely on radio emissions from clouds of hydrogen gas and the motions of distant satellites to infer the velocities there. Gaia's precise measurements have improved our models, but the outermost parts of the curve remain elusive. Some data even suggest small deviations, ripples, and asymmetries that hint at interactions with passing dwarf galaxies or clumps of dark matter. The Milky Way's rotation is not perfectly uniform. It carries scars from its past. Each merger and gravitational encounter leaves a subtle imprint on the dance of its stars, like eddies in a vast cosmic current. These variations offer a new way to probe the distribution of dark matter. By studying where the rotation curve rises, dips, or flattens, scientists can infer how masses spread throughout the galaxy. Yet, while dark matter explains the flat rotation curves beautifully, it opens deeper theoretical questions. Why does every galaxy seem to exhibit the same pattern, regardless of size or luminosity? Some researchers propose that this consistency points to a universal property of gravity itself. Modified Newtonian dynamics, MOND, a controversial alternative theory, suggests that at extremely low accelerations, gravity behaves differently than our equations predict. In this model, the flat rotation curves arise not from invisible matter, but from a change in the law of motion at galactic scales. For decades, astronomers have tested these ideas, weighing the elegance of dark matter against the simplicity of modified gravity. So far, dark matter remains the favoured explanation, but the debate underscores how little we truly understand about the universe's fundamental workings. The Milky Way's own rotation adds further intrigue. Our Sun, for example, moves at about 220 kilometers per second around the galactic centre, yet its orbit is remarkably stable, even though it is influenced by billions of neighbouring stars and the invisible sea of dark matter. The balance between motion and gravity is precise beyond comprehension, a cosmic harmony sustained over billions of years. The rotation curve also defines the galaxy's escape velocity, the speed required for an object to break free from its gravitational pull. Near the Sun's position, that speed is around 550 kilometers per second. Anything moving faster will eventually drift into intergalactic space, though in practice, few objects achieve such velocity. A handful of hypervelocity stars have been observed doing just that, likely flung from the galactic centre by interactions with the supermassive black hole. Their trajectories provide further tests of the Milky Way's gravitational profile, tracing how the rotation curve extends into the outermost halo. These measurements reveal that even at 500,000 light-years from the centre, the galaxy's grip remains strong proof that its dark matter halo continues far into the void. The rotation curve mystery, once a shocking anomaly, has evolved into a cornerstone of cosmology. It is both a map and a message, showing that the universe is built upon unseen foundations. The motion of stars, so elegant and predictable, hides a profound truth. Most of what governs their fate is invisible. Each orbit, each swirl of gas, each spiral arm testifies to the presence of a shadow realm of mass. We measure it not by light, but by motion, reading the invisible script written in the stars. And in that script lies one of the deepest lessons science has ever uncovered, that the universe we see is only a small fraction of the one that truly exists. For centuries, humanity has imagined the Milky Way as an elegant spiral, a graceful pinwheel of light turning silently in space. Artists painted it with sweeping arms curving around a brilliant core, each arm defined and symmetrical, glowing with newborn stars. Yet as our instruments grew more powerful, this comforting image began to dissolve. The real Milky Way, as modern astronomy reveals, is far more complex, far less orderly, a living structure of turbulence, distortion, and hidden motion. Its spiral arms are not solid features etched into space, but transient patterns, waves of density moving through the galactic disk like ripples across water. Within these waves, gas clouds compress and ignite, forming new generations of stars, which in turn illuminate the arm before drifting away into the darker regions between. What we call the arms are therefore not fixed pathways of matter, but dynamic regions where gravity and motion conspire to create the illusion of permanence. Mapping these spirals from within the galaxy is a monumental challenge. From our vantage point near the middle of one arm, the rest of the structure stretches outward in every direction, obscured by dust and gas. For much of the 20th century, astronomers believed the Milky Way had 4 major arms: the Perseus, Sagittarius, Scutum Centaurus and Norma arms, each winding outward from the central bar like the limbs of a starfish. But newer data from the Gaia mission, combined with radio observations of hydrogen and molecular clouds, suggest a more intricate and uneven form. Some arms split, merge, or fade into faint extensions. Others, once thought distinct, may not exist as continuous features at all. The Milky Way's structure appears lopsided, one side heavier and more extended than the other, possibly due to past interactions with dwarf galaxies that tugged unevenly on its mass. Even the galactic bar, a dense, elongated cluster of stars at the centre, seems to twist the inner spiral pattern, driving waves of star formation that ripple outward. The more precisely we map the Milky Way, the less symmetrical it becomes. The spiral we once imagined as smooth and orderly is, in truth, warped, with its outer disk bending upward on one side and downward on the other like a bent vinyl record. This warp may have been caused by gravitational encounters with the Sagittarius dwarf galaxy, which the Milky Way has been steadily consuming over billions of years. Each pass of that smaller system through the galactic plane creates ripples, like stones dropped into a pond, leaving the disk oscillating long after the impact. These deformations are subtle but far-reaching, visible only through careful measurement of millions of stars. They remind us that the Milky Way is not a static picture, but a moving symphony, its shape constantly changing as forces act upon it. Hidden within this complexity are structures even stranger. Between the spiral arms lie vast gaps filled with older stars, known as interarm regions. In these dark spaces, the processes of starbirth slow, and the remnants of ancient stellar generations drift in quiet orbits. Threaded through the entire disk is a network of filaments and bubbles, supernova remnants, shock waves, and magnetic fields twisting the gas into intricate patterns. Above and below the disk stretch two enormous plumes of energy known as the Fermi bubbles, each thousands of light years tall. These massive outflows, detected in gamma rays, hint at past eruptions from the supermassive black hole at the galaxy's core. They are silent evidence that the Milky Way is not merely rotating but breathing exhaling energy and matter into the surrounding halo. When we look toward the galactic centre, the brightness hides this underlying chaos. Billions of stars overlap, their light blending into a luminous fog. Yet beneath that brilliance lies a churning gravitational engine, sculpting the spiral from within. Even the pattern of our local region, the Orion arm where the Sun resides, is deceptive. It is not a true arm at all, but a small spur and offshoot connecting two larger structures. Our solar system occupies a minor feature in a vast irregular tapestry. To imagine the Milky Way as a simple symmetric spiral is like describing an ocean by its surface alone. Its beauty lies in its motion, its imperfection, and its constant reinvention. Each arm is a wave, each wave a cycle of birth and decay. Stars form, shine, and die, their remains seeding the next generation, keeping the pattern alive. This perpetual transformation defines the galaxy's character more than any static shape. The hidden structure of the Milky Way, unravelled by modern science, is not less beautiful for its complexity, it is more so. In its asymmetry, in its warps and filaments, in the invisible currents of dark matter guiding its form, we find a deeper truth. That order in the cosmos is not the absence of chaos, but its harmony. The Milky Way is a living entity of gravity and time, a grand improvisation that has been unfolding for billions of years. And as we continue to chart its spirals and secrets, we are reminded that the universe's most intricate designs are never fixed. They are alive, constantly reshaping themselves in the endless rhythm of creation. When scientists speak of the Milky Way's edge, the word carries an illusion of precision that reality refuses to honour. Galaxies do not end like cliffs or coastlines. They fade gradually, dissolving into the surrounding cosmic dark. For decades, astronomers tried to pinpoint where the Milky Way stops, but every attempt revealed only how ambiguous that notion truly is. Early maps defined the edge as the distance beyond which starlight thinned into blackness, roughly 50,000 light-years from the centre. Later surveys pushed that boundary to 100,000, then 200,000. Each improvement in technology, each deeper observation, extended the known frontier further outward. Today, we understand that there is no single definitive boundary-only overlapping layers of structure that grow increasingly diffuse with distance. The Milky Way's visible disk of stars, gas and dust blends into a vast stellar halo populated by ancient suns and faint clusters. Beyond that lies an even larger halo of dark matter, invisible yet immensely influential, stretching nearly 1 million light-years across. Somewhere within that gradient we must draw a line for the sake of definition, but nature does not draw it for us. The edge depends entirely on what we choose to measure: light, mass, gravity, or gas. If one defines the galaxy by the distribution of bright stars, its edge lies near the limits of the stellar disk. If one defines it by gravitational influence, it extends until the Milky Way's pull gives way to that of Andromeda. In truth, those two definitions differ by hundreds of thousands of light-years. The concept of an edge becomes philosophical rather than physical. The galaxy does not stop. It simply fades into the larger structure of the universe. Even within the disk, the transition from the bright spiral arms to the outskirts is gradual. The density of stars falls smoothly, not abruptly, and the gas becomes more tenuous, forming wisps that stretch into intergalactic space. Radio telescopes have traced hydrogen far beyond the optical limits, revealing that the Milky Way's gaseous envelope continues well past where the light of stars disappears. Some of this material is primordial, left over from the galaxy's formation. Some has been stripped from passing dwarfs, or recycled through supernova winds. The edge, in this sense, is a moving frontier, constantly reshaped by inflows and outflows. New matter falls inward, while energetic events from within push other material out. The boundary of the Milky Way is not a wall but a breathing membrane between the galaxy and the intergalactic medium. It is where gravity and emptiness negotiate their uneasy balance. The difficulty of defining the edge is not just an observational challenge, it is a conceptual one. We like to think of objects as distinct, separated from their surroundings, but galaxies defy that simplicity. They are part of a cosmic ecosystem, their halos and gas streams overlapping, exchanging matter like tides between islands. Our own Milky Way interacts constantly with nearby companions, drawing material from the Magellanic Clouds and tugging at faint dwarfs on its outskirts. Even the gravitational reach of Andromeda presses upon it. The two galaxies' dark halos already intermingle, blurring the line between one system and the next. In a very real sense, the Milky Way is not an isolated entity, but a region within a larger gravitational landscape, the Local Group, a cluster of more than 50 galaxies bound together by shared mass. Where then does the Milky Way end and the universe begin? Perhaps the better question is whether that distinction means anything at all. When we observe the outermost halo stars, some orbiting 500,000 light-years from the centre, we might call them part of the galaxy. Yet their orbits are so vast that they will never complete even a single revolution in the age of the universe. Are they truly members of the Milky Way, or wanderers bound only by chance? Our definitions are conveniences, not truths. Even the term edge is misleading. It implies limitation, when the galaxy is anything but limited. It is a continuum of matter, energy, and gravity extending indefinitely outward, merging into the cosmic web. Every galaxy shares this property, each one a knot in an endless network of connection. The more we learn, the clearer it becomes that edges exist only in our minds. Still, defining one has practical importance. To understand how galaxies form and evolve, we must decide where they begin and end. For measurement, for modelling, for comparison, we impose artificial borders, yet we must never mistake those boundaries for reality. The Milky Way's true edge is a gradient of influence, not a line of demarcation. It is where light fades but gravity endures, where the known dissolves into the infinite. And perhaps that is fitting, for a galaxy's edge mirrors our own pursuit of knowledge, always reaching outward, never arriving at a final limit, only finding new depths to explore beyond what we once called the end. At the farthest reaches of the Milky Way, where the glow of the spiral disk fades into darkness and the gravitational grip begins to loosen, a rare and remarkable population of stars defies expectation. These are the high-velocity halo stars, stellar wanderers moving at incredible speeds, some fast enough to nearly escape the galaxy entirely. Their existence tells a story of violence, motion, and the unseen forces that shape our cosmic home. Most stars within the Milky Way follow predictable orbits, bound by the galaxy's gravity into long, graceful ellipses. But every so often, astronomers find one racing through space like a bullet, moving hundreds of kilometers per second faster than its peers. These hypervelocity stars, as they're called, are the outliers in the galactic dance. They live on the edges of stability, their trajectories slicing through the vast halo, and in some cases extending into intergalactic space. The first of these extraordinary stars was discovered in 2005, its speed so extreme that it could not be explained by normal orbital motion. Since then, dozens more have been found, and their origins have become one of the great detective stories of modern astrophysics. One leading theory traces their acceleration to the Milky Way's central black hole, Sagittarius A, a monstrous object 4 million times the mass of the Sun. Near its event horizon, gravity warps space-time so severely that any close encounter can fling matter outward at extraordinary velocities. If a binary star system wanders too near the black hole, the intense tidal forces can tear it apart, one star captured, the other hurled outward like a stone from a slingshot. Such a star becomes a hypervelocity traveller, ejected from the galactic core at speeds exceeding 1,000 kilometers per second, fast enough to break free from the Milky Way's pull. As it races outward, it carries with it a record of its violent birth, a lonely exile from the heart of the galaxy. Yet not all high-speed stars originate from the centre. Some are flung outward during supernova explosions when one star in a binary detonates, propelling its companion into space. Others may be remnants of ancient mergers, relics of dwarf galaxies long consumed by the Milky Way. Their motions through the halo trace invisible currents of gravitational history, marking the scars of past collisions. Gaia's precise tracking of stellar motion has revealed that many of these stars are older than the galaxy's thin disk, suggesting they belong to an ancient population formed in smaller systems before being assimilated. Their orbits are chaotic and elongated, some plunging deep through the galactic plane before soaring back into the outer halo. By studying their trajectories, astronomers can map the gravitational potential of the Milky Way with unprecedented accuracy, using these stars as test particles to probe the shape and mass of the dark matter halo. The speed and direction of each one carry clues about the distribution of unseen matter. A star moving slightly faster or slower than predicted can indicate regions where dark matter clumps more densely, creating subtle distortions in gravity's smooth field. Thus, these fugitives from the galactic norm have become essential tools for studying the invisible. Their existence also challenges our understanding of the Milky Way's boundaries. If some of these stars achieve true escape velocity, they will drift endlessly into intergalactic space, carrying the galaxy's material with them. In this way, the Milky Way continually loses a trickle of stars, a slow evaporation into the void. Over billions of years, such losses may subtly alter the galaxy's balance, redistributing its mass and energy. Yet most high-velocity stars remain bound, their speed great but not infinite. They form a kind of halo chorus, perpetually in motion, tracing paths that cross the unseen architecture of dark matter. Their presence at the galactic frontier demonstrates the Milky Way's enduring gravitational strength. Even stars moving faster than 500,000 kilometers per hour often cannot escape its hold. They serve as living boundaries, marking the region where gravity's grip weakens but never quite lets go. To observe them is to witness the tension between freedom and constraint on a cosmic scale. These stars, exiled yet tethered, embody the dynamic nature of the galaxy itself, a system in constant flux, where motion defines identity and boundaries blur into the infinite. Some astronomers speculate that similar populations must exist in other galaxies, each one scattering its own emissaries into the darkness. In the vast silence between galaxies, such stars may wander alone for eternity, their faint light the last echo of a civilization's home galaxy. They are cosmic messengers testifying to the forces that rule both the visible and invisible realms. In studying them, we glimpse not only the Milky Way's power, but also its fragility, its gradual dispersal into the universe it inhabits. Each high-velocity star is a reminder that nothing in the cosmos is truly still, that even in the outermost reaches of our galaxy, motion is eternal, and the line between belonging and escape is as fluid as the starlight that fills the dark. The revelation that our own galaxy is twice as large as once believed did more than correct a measurement. It cracked open the foundations of cosmic understanding. For decades, astronomers assumed that the Milky Way's dimensions were well known, its mass and scale serving as reference points for the study of other galaxies. If we could not accurately gauge the structure of the one we live in, then how certain could we be about any of the others? The recognition that our galactic map was so incomplete triggered a profound re-evaluation of nearly everything we thought we knew about the universe. If the Milky Way's size, mass and halo had all been underestimated, then the same systematic errors might extend across countless observations. Every galaxy we've measured was mapped through the same set of assumptions, luminosity-based distances, rotational modelling, and brightness thresholds that fade into darkness. What if every one of those galaxies is larger, heavier, and more complex than our data suggest? The consequences ripple outward like shockwaves. Our models of galactic evolution, gravitational interactions, and cosmic distribution all depend on accurate scaling. Double the average size of a galaxy, and you double its gravitational influence, its dark matter, content, its role in shaping nearby systems. The universe, in that light, becomes denser and more connected than previously believed. The vast voids between galaxies might not be as empty as they seem. Halos and gas envelopes could overlap across immense distances, binding the cosmic web even tighter. This new perspective reshapes the very concept of isolation in space. What we once called separate galaxies may in truth be overlapping domains of influence, their invisible halos blending in subtle exchanges of mass and energy. The discovery also forces a reconsideration of the so-called missing mass problem, the discrepancy between the amount of matter predicted by cosmological models and what we actually detect. If galaxies are larger and heavier, much of that missing matter may already be accounted for, hidden not in deep space but in the uncharted outskirts of structures we thought we knew. The implications extend to cosmology itself. Our estimates of dark matter and dark energy depend heavily on how we calculate the universe's mass distribution. Revising galactic sizes could shift those ratios, altering the inferred expansion rate of the cosmos. Even the age and evolution of large-scale structures might need recalibration. The universe, once thought to be racing toward eternal acceleration, may behave differently when its true mass is properly counted. Every recalculation introduces new complexity, but also a deeper truth. The cosmos is more intricate than our simplified models allow. The shift in understanding also touches philosophy as much as physics. For centuries, humanity has oscillated between overestimating and underestimating its place in the universe. The discovery of a larger Milky Way is both humbling and empowering. It reminds us of the vastness that surrounds us while reaffirming our capacity to uncover it. The act of correction itself is proof of progress. Science evolves not through certainty but through revision, and each discovery expands both knowledge and mystery. When astronomers realized that our galaxy was far larger, they did not despair at past errors. They marveled that reality could still surprise them. The recalibration of the Milky Way also redefines how we view the cosmos as a living, interconnected system. Galaxies are not isolated machines, but dynamic participants in a grander cosmic ecosystem. Their halos overlap, their gas exchanges, their motions choreographed by gravity on scales that defy comprehension. If we have misjudged their boundaries, it may mean that the universe is even more relational than we thought, its vast spaces filled not with emptiness, but with invisible threads linking one world to another. This realization blurs the boundary between galaxy and universe, suggesting that the two are not distinct categories, but degrees of the same continuum. The more we learn, the less the universe resembles a collection of separate objects, and the more it appears as one immense, entangled whole. Even light itself, once thought the clean measure of distance, now seems inadequate. Dust, gas, and time distort its message, forcing us to interpret rather than merely observe. Rethinking the universe means accepting that every image, every map, is provisional. What we call the known universe is just the portion bright enough for our current instruments to detect. Beyond that, the unseen may be far greater than we imagine, not only in size but in structure, richness, and depth. This is not a defeat, but a liberation, an invitation to continue the search with renewed humility. The cosmos we thought we had measured turns out to be immeasurable. The order we thought we had charted gives way to a deeper, more intricate harmony. To rethink the universe is to understand that discovery is endless, that certainty is temporary, and that the horizon of knowledge recedes as fast as we approach it. The Milky Way's true size is not merely an astronomical fact, it is a reminder that even our most trusted maps are drafts of a universe still being written. For generations, astronomers believed that the Milky Way's centre was a fixed point, an unshakable anchor around which all else revolved. In diagrams, it was drawn as a brilliant core, an axis of stability amid the galaxy's vast rotation. But as our measurements became more precise, that assumption began to fracture. The true centre of the Milky Way, it turns out, is not perfectly stationary, nor is it defined solely by the supermassive black hole known as Sagittarius A. Instead, it is a dynamic point, a shifting balance of mass, motion and energy. The heart of the galaxy is alive, trembling under the weight of billions of stars, vast clouds of gas, and the immense gravitational tides of its bar and spiral arms. The black hole at the centre may contain 4 million solar masses, but the surrounding bulge holds hundreds of billions, creating a gravitational seesaw where equilibrium is constantly renegotiated. Sagittarius AE itself wobbles, pulled slightly by the orbits of nearby stellar clusters, its position shifting subtly over time. To us, these motions are nearly imperceptible, yet they reveal that the galactic core is not a monolithic engine but a living, vibrating nexus of gravity. The idea of a moving centre challenges our intuitive sense of cosmic order. We like to think of galaxies as mechanical systems with predictable centres of rotation, but in reality their cores are chaotic, dense, with stars moving at thousands of kilometres per second, colliding, merging, and flinging one another through complex gravitational interactions. Within the central few light-years of the Milky Way, stars orbit so rapidly that they complete a full revolution in mere decades. Some travel on elliptical paths so extreme that they brush dangerously close to the black hole before slingshotting back into the surrounding bulge. These orbits, measured with exquisite precision by instruments like the Very Large Telescope and the Keck Observatory, provide direct proof of the black hole's mass and nature. Yet even they reveal irregularities, tiny deviations hinting at the presence of other gravitational influences, perhaps intermediate mass black holes or dense clusters of dark matter. The galactic centre, once thought to be a single object, is instead a crowded city of gravity, full of invisible citizens whose collective pull keeps the entire system in motion. This mobility extends beyond the immediate core. The Milky Way's bar, a long, rotating structure of stars that spans thousands of light-years, acts like a gravitational lever, redistributing mass and energy through the galaxy. As the bar turns, it channels gas inward toward the centre, fueling waves of star formation and feeding Sagittarius A. The influx of matter can temporarily brighten the core, transforming the galaxy's heart into an active nucleus before subsiding again. Each cycle shifts the balance of forces slightly, altering the position of the galaxy's true centre of mass. In a sense, the Milky Way breathes its heart pulsing not with blood but with gravity. Even the Sun's orbit, so seemingly stable, is influenced by these subtle shifts. Over millions of years, the galactic centre's gravitational focus moves just enough to cause the plane of our solar system's orbit to oscillate slightly, creating long-term variations that may even influence the distribution of comets in the Oort cloud. The notion that our galaxy's heart moves, however slightly, invites a deeper philosophical reflection. If even the centre of the Milky Way is not fixed, what is? The universe, it seems, abhors stillness. Every point, from the smallest particle to the largest cluster of galaxies, exists in perpetual motion, responding to forces both near and far. The Milky Way's centre is simply the most dramatic example of this truth, its balance shifting as stars are born and die, as matter flows inward and outward, as the galaxy continues its long dance toward collision with Andromeda. These subtle wobbles may even hold clues to cosmic history. Some astrophysicists believe the centre's uneven motion carries the memory of past mergers, the lingering echo of smaller galaxies swallowed long ago. Each ingestion may have displaced the core slightly, its gravitational focus migrating as new mass was absorbed. Over billions of years, these minute shifts accumulate, giving the Milky Way a restless heart that never truly settles. To map that movement is to trace the galaxy's evolution itself. In recent years, Gaia's high-precision data has allowed astronomers to detect minute drifts in the positions of stars near the centre, confirming that the gravitational midpoint of the Milky Way is indeed offset by a small but measurable amount. It is as if the galaxy spins not around a single point, but around a fluctuating centre of gravity that drifts like the eye of a storm. This revelation does not diminish the grandeur of the Milky Way. Rather, it deepens it. It shows us that even in the seeming stillness of the cosmic order, there exists motion, interplay, and change. The centre is not an anchor but a heartbeat, a pulse that echoes through the spiral arms, keeping the galaxy alive in its endless, graceful rotation. Galaxies are not serene, isolated islands drifting through space. They are restless, social, and violent by nature. Every grand spiral and every luminous elliptical is the product of countless collisions, each encounter leaving scars and beauty in its wake. The Milky Way is no exception. Its tranquil appearance belies a turbulent history written in the motions of its stars, the ripples in its disk, and the ghostly remnants of galaxies it has devoured. Our galaxy is, in truth, a mosaic of mergers, an amalgamation of once independent systems absorbed over billions of years. When two galaxies meet, they do not crash like solid objects. Their stars are so far apart that direct collisions are rare. Instead, they pass through each other like ghosts, their mutual gravity pulling and twisting them into new forms. Gas clouds collide and compress, triggering explosive bursts of star formation, while tidal forces stretch each galaxy into elongated streams of stars that can persist for eons. These encounters are both destructive and creative, dismantling old structures even as they forge new ones. The Milky Way has consumed dozens of smaller galaxies, and evidence of those meals can still be seen today. Faint, stellar streams, like the Sagittarius Stream and the Helmy-Debris Arc across the sky, each a remnant of a dwarf galaxy torn apart by our own. Gaia's precise mapping of stellar motion has revealed dozens of such traces, showing that the Milky Way's halo is a graveyard of ancient mergers. These remnants are not mere curiosities, they are records of the galaxy's growth, fossils that preserve its evolutionary timeline. By studying their orbits, compositions, and ages, astronomers can reconstruct the sequence of events that built the Milky Way. Some of the oldest halo stars may predate the galaxy itself, survivors from primordial clusters that merged to form its foundation. Each collision added not just stars and gas, but also dark matter, expanding the invisible halo that anchors the entire structure. The process continues even now. The Sagittarius dwarf galaxy, a faint companion orbiting our own, is currently being shredded by tidal forces. Its stars are being stretched into a vast ribbon encircling the Milky Way, gradually blending into the disk. Other small galaxies, such as the Large and Small Magellanic Clouds, are spiraling inward on similar fates, their gravity tugging on our galaxy's outskirts, distorting the disk and fueling new waves of star formation. These ongoing interactions remind us that galactic evolution is not finished. It is a living, continuing process. The ultimate and most dramatic collision awaits some 4 billion years in the future, when the Milky Way and Andromeda will meet. The two giant spirals are already drawing toward each other, their dark matter halos intertwined. When they collide, the night sky will transform beyond imagination. The galaxies will pass through one another multiple times, their shapes distorted into long tidal tails. Their central black holes will spiral inward, eventually merging in a cataclysmic burst of energy that may outshine the rest of the universe. Over time, their stars will settle into a new form, an enormous elliptical galaxy, often called Milkomeda. For the stars themselves, the collision will not be apocalyptic. The vast emptiness between them ensures that few will actually collide, but their orbits will change dramatically, and any surviving planetary systems will experience new skies filled with unfamiliar constellations. The solar system, if it still exists then, will drift into a new galactic configuration under an altered gravitational field. Yet from destruction will come creation. The merger will compress gas clouds, igniting new starbursts and seeding fresh generations of suns. The cycle of death and birth that defines the universe will continue, reshaping chaos into beauty. Galactic collisions also play a crucial role in cosmic ecology. They drive evolution by mixing materials, spreading heavy elements forged in old stars into new regions, enriching future planets with the ingredients for life. Without these colossal interactions, the universe would remain chemically primitive. Every atom of carbon, oxygen, and iron on Earth likely owes its existence to a long chain of stellar deaths and galactic mergers. Thus, the violence of collisions is the engine of creation. They do not mark the end of galaxies, but their renewal, ensuring the cosmos remains dynamic rather than static. Observations of distant galaxies show that such interactions were far more common in the early universe, when space was smaller and systems lay closer together. The Milky Way itself was born amid that frenzy, shaped by forces that still echo today. Each ripple in its disk, each asymmetry in its spiral arms, carries the memory of an encounter. Even now, the gravitational pull of approaching neighbours subtly alters its motion, whispering of the inevitable future when those whispers will become a roar. The story of galactic collisions is not a tragedy. It is the heartbeat of creation. In their immense violence lies the artistry of the universe, the eternal interplay of gravity and light that builds, destroys, and rebuilds. Through collisions, galaxies remember that they are not alone, and in their merging they write the next chapter of cosmic evolution, a reminder that creation, in all its forms, is born from movement, contact, and change. The Milky Way's story is far from finished. It stands in the middle of its cosmic life, neither young nor old, still changing, still alive with the restless rhythm of creation. Though we perceive it as timeless and eternal, the galaxy is evolving even now, reshaping itself under the persistent influence of gravity, star formation, and cosmic interaction. Every new measurement, every improved simulation, paints a picture of a future both magnificent and inevitable, a future defined by transformation. In the short term, over the next few 100 million years, the Milky Way will continue its slow spiral, its arms winding gracefully as stars are born and die in cycles that maintain a delicate balance of energy. The galactic bar at its core will twist more tightly, feeding gas towards Sagittarius A, perhaps awakening the central black hole from its current dormancy. When that happens, the Milky Way could briefly flare into brilliance, becoming an active galaxy, its centre glowing with powerful jets and X-rays as matter falls inward and releases tremendous energy. The outburst would not threaten the sun, far from the heart of the storm, but it would transform the appearance of the night sky, painting it with streams of ghostly light visible across tens of thousands of light years. Over longer spans of time, hundreds of millions to billions of years, the galaxy's structure will shift dramatically. Star formation will gradually slow as the available gas is consumed or expelled. The spiral arms will grow fainter, their bright young stars giving way to older, cooler populations. The Milky Way will begin to age, settling into a more quiescent phase of existence. Yet even as internal processes fade, external forces will rise to prominence. The Magellanic Clouds, drawn inexorably inward, will merge with our galaxy, triggering new bursts of star formation and altering the shape of the disk. Their accretion will add mass to the halo and stir the outer regions, sending ripples through the galactic plane that may persist for eons. Then, in roughly 4 billion years, the greatest event of all will occur, the collision with Andromeda. Long before the actual impact, the galaxy's halos will interact, their outer gas clouds merging and exchanging material. As they draw closer, the night sky from Earth or whatever world survives in its place will change beyond recognition. The faint smudge of Andromeda will expand into a brilliant spiral filling the heavens, its structure visible to the naked eye. Over millions of years it will grow brighter until the two galaxies begin their gravitational embrace. The collision will unfold in slow motion, lasting several billion years from first contact to final merger. Stars will be flung into vast tidal streams, reshaping both galaxies into spectacular arcs of light. Planetary systems will drift through seas of unfamiliar stars, their skies lit by thousands of suns. Eventually, the cores of both galaxies will merge, and their central black holes will spiral together in a gravitational dance, radiating waves through space-time before uniting into one colossal singularity. When the dust settles, the new galaxy, often imagined as an enormous elliptical, will shine brighter than either progenitor, its forms smooth and golden with age. Astronomers have already named this future creation Milkomeda. Though the collision will erase the spiral form of the Milky Way, it will also bring renewal. The compression of gas during the merger will ignite new starbursts, producing fresh generations of suns and planets. For a time, Milkomeda will blaze with youthful vigour, a cosmic phoenix rising from the ashes of its ancestors. Over the next tens of billions of years, star formation will eventually cease altogether as the gas supply dwindles. The galaxy will grow dimmer, filled mostly with red dwarfs, white dwarfs, neutron stars and black holes, the remnants of long-dead stars. The universe itself will continue to expand, carrying other galaxies farther and farther away, until Milky drifts alone in an ever-darkening void. In the far future, perhaps 100 billion years from now, distant observers within this merged system, if any remain, will no longer be able to see the larger universe beyond. Cosmic expansion will have pushed the rest of the galaxies beyond the horizon of light. To them, Milky will appear to be the entire universe, its own stars the only ones left in existence. In that sense, our galaxy's future is not merely a tale of transformation, but a meditation on impermanence. Everything changes from the smallest atom to the grandest structure. The Milky Way was born from collisions and will end in one, its light eventually fading into the cosmic background. Yet its legacy will endure in the atoms scattered into space, in the structures it helped shape, in the endless continuity of matter and energy. The galaxy's fate is a reminder that endings in the universe are never truly final. They are transitions, part of an eternal cycle of collapse and renewal. When we gaze at the Milky Way's soft glow across the sky, we are witnessing both a memory and a prophecy, a living thread in the cosmic tapestry that began long before us and will continue long after we are gone. For all its staggering immensity, the Milky Way is also deeply personal. It is the backdrop of every human story ever told, the celestial river that has flowed silently above us since the dawn of consciousness. Long before telescopes, long before science itself, people looked up at its glowing band and wondered what it meant. They gave it names and myths, called it the Path of Souls, the Spine of Night, the Silver Road. To the ancient Greeks, it was the milk of the goddess Hera. To the Chinese, the celestial river separating the lovers Niulang and Xinu. To countless other cultures, it was a bridge between the mortal and divine. For millennia, the Milky Way was a symbol of mystery, eternity, and belonging. It connected Earth to the heavens, suggesting that we are part of something greater, something infinite. Only in the last few centuries have we come to understand that this shimmering trail is not a cloud or a spirit road, but the collective light of hundreds of billions of stars, each a sun, each perhaps with its own worlds and possibilities. That realization, far from diminishing its majesty, deepened it. The Milky Way became not just a sight of beauty, but a revelation of scale. To see it clearly is to feel the dual weight of wonder and humility. Our ancestors saw the same stars and felt awe. We see them and grasp, however faintly, the immensity of what we inhabit. The more we learn, the more our perspective expands, and yet the feeling remains the same, a recognition that we are both infinitesimal and integral to the cosmos. Science has transformed the Milky Way from a mythic symbol into a physical reality. Yet in doing so, it has also given it new layers of meaning. We now know that every atom in our bodies was forged in the hearts of ancient stars, many of them long gone, their remains scattered through the galaxy before coalescing into the Sun and Earth. The Milky Way is not just a place we observe from afar, it is our origin, our home, our inheritance. The hydrogen in our blood once drifted in the cold galactic clouds that gave birth to the Sun. The iron in our veins was born in supernovae that exploded before the Earth even existed. In the grand sense, we are the Milky Way made conscious, the universe examining itself through living eyes. Yet with that knowledge comes responsibility and fragility. Our species, perched on a small planet in an ordinary star system on the outskirts of a single spiral arm, has only recently begun to comprehend its place. We are newcomers to cosmic awareness, and already our actions reach beyond our planet's surface, altering climates, sending probes into interstellar space, and transmitting messages to the stars. For the first time, the Milky Way contains beings capable of understanding its structure, its history, and even its destiny. Whether that understanding will endure depends on our ability to survive long enough to become true citizens of the galaxy. When we gaze at the Milky Way, we're not merely looking outward, but inward. Every scientific discovery about it reflects something about ourselves, our curiosity, our persistence, our need to find meaning in the infinite. Each telescope we build, each mission we launch, extends our senses deeper into that cosmic river, showing us that the universe is neither hostile nor kind, it is indifferent but knowable. The light that reaches us tonight may have begun its journey before humans existed, yet we are here to receive it, to interpret it, to fold it into the story of what it means to be alive. As our technology advances, our view of the galaxy grows sharper and more complete. yet the emotional response remains unchanged. Awe, humility, wonder. These are constants of the human spirit. Whether through myth or mathematics, we are drawn to the Milky Way because it embodies the tension between the finite and the infinite. It is both a reminder of our smallness and an affirmation of our capacity to understand what once seemed beyond comprehension. One day, perhaps, our descendants will travel beyond the solar system, settling among the stars that now appear as faint dust across the night sky. To them, the Milky Way will no longer be a distant spectacle, but a familiar landscape, their home stretching from one arm to another. And yet, even then, the feeling will persist, the same quiet awe that filled the hearts of our earliest ancestors who first looked up and named that glowing trail of light. The galaxy will continue to inspire questions, stories, and dreams, uniting science and wonder as two faces of the same impulse to reach for the infinite. The Milky Way does not just surround us, it defines us. It is the thread connecting our past to our future, a bridge between imagination and knowledge. To understand it is to glimpse eternity. To belong to it is to know that we are part of something vast, mysterious, and enduring. In every sense, the Milky Way is both our origin and our destiny. A mirror held up to the infinite, reflecting back the light of our brief and brilliant existence. The Milky Way is not a static structure frozen in space. It is a living, breathing system, dynamic, responsive, and evolving. Every part of it, from the glowing heart at its center to the faintest hydrogen cloud at its edge, participates in a vast circulation of matter and energy. Stars are born, live, and die, returning their enriched material to the interstellar medium, which in turn gives rise to new stars and planets. Gas flows inward, feeding the galactic core, while other streams are expelled outward through supernova winds, forming immense bubbles that rise into the halo. Gravity binds everything together, yet within that bond exists constant motion. The Milky Way behaves less like a machine and more like an organism complex, self-regulating and perpetually renewing itself. At its core lies a vast feedback loop. Matter collapses to form stars. Stars forge heavy elements, and when they die, they release those elements back into the galaxy, enriching the material from which the next generation will form. This cycle is repeated uncounted times, transforming the galaxy from a primordial cloud of hydrogen and helium into the intricate ecosystem we observe today. In a very real sense, the Milky Way evolves chemically and structurally, becoming more complex with every rotation. Regions of intense star formation known as stellar nurseries serve as the galaxy's beating heart. These regions, dense with gas and dust, pulse with creation. Massive stars ignite, their ultraviolet radiation sculpting the surrounding clouds into glowing shapes. When those stars end their lives in supernovae, they send shockwaves that compress nearby gas, sparking new rounds of formation. Thus, one generation gives birth to the next, an endless succession of creation and destruction that sustains the galactic rhythm. The Milky Way's magnetic fields and cosmic rays also play vital roles in this equilibrium, threading through the interstellar medium and influencing how matter collapses and moves. Even the vast dark matter halo contributes to this living balance, providing the gravitational skeleton upon which all visible activity depends. Though invisible, dark matter dictates the tempo of galactic life, guiding the flow of gas and stars in unseen harmony. The Milky Way is not uniform. It is patchy, textured, and full of gradients. Some regions teem with hot young stars and energy, while others drift in quiet stasis. Yet all are connected through a continuous flow. Gas expelled from one area eventually cools and falls back toward the disk, a galactic rain that sustains star formation over time. On immense scales, the galaxy recycles itself, its matter forever moving in vast cosmic currents. Even star death contributes to renewal. White dwarfs, neutron stars, and black holes, once endpoints, become anchors for new structures, distorting space, accreting gas, and influencing the orbits of their neighbours. The galaxy is not decaying but transforming, every end feeding a beginning. Astronomers now speak of galactic metabolism, a term once poetic but increasingly literal as we learn how energy and material circulate through space. Observations from telescopes like Gaia, Chandra, and Alma have revealed how outflows from the central regions feed the halo, how stellar winds shape the spiral arms, and how gravity and radiation together maintain equilibrium. Even the enormous Fermi bubbles that rise above and below the galactic plain giant lobes of gamma-ray emission, stretching 25,000 light-years each, are part of this grand metabolic system. They testify to ancient eruptions from the black hole at the galaxy's core, bursts of energy that reshape the surrounding medium and may still influence star formation today. The galaxy lives through such pulses, moments of activity followed by long periods of calm. Over billions of years, this balance of stability and upheaval has allowed the Milky Way to endure while continually reinventing itself. It is a system that both preserves and transforms, never truly at rest. To view it this way is to move beyond the mechanical metaphor of spinning disks and orbits, and to see instead the living complexity of cosmic ecology. The Milky Way is not a collection of parts. It is a single, vast, interconnected being. Every atom, every photon, every gravitational wave participates in its ongoing evolution. We too are part of that system. The atoms that compose our bodies were once part of stars that lived and died within this galactic cycle. The oxygen we breathe and the carbon we exhale flow back into the interstellar medium, joining the endless exchange. When humanity looks outward, it is not observing something separate but something of which it is a continuation. The galaxy is alive, and through us, it knows itself. In this way, the Milky Way is more than a structure. It is an expression of cosmic continuity, a reminder that even across unimaginable scales, the universe is not inert but deeply, profoundly alive. The Milky Way's spiral arms are more than graceful patterns of light. They are the very rhythm of the galaxy's existence, the endless pulse that defines its identity. They are not solid entities but waves of density, perpetual spirals of motion through which stars and gas flow like blood through arteries. The arms rotate not as rigid structures but as living patterns that move at their own pace, independent of the stars they carry. In this sense, the galaxy's spiral form is an illusion of stability, a momentary shape held together by motion and gravity. Yet within that illusion lies profound truth. The spiral is eternal, not because it remains the same, but because it is always becoming. The stars within it are transient participants in a dance older than themselves. Each generation of stars is born within the arms, lives its life and dies, while the spiral pattern endures, perpetually renewed by the flow of matter through its curves. The spiral is thus both an image of impermanence and a symbol of continuity. It represents the dynamic equilibrium that sustains the galaxy, where creation and destruction balance in endless rhythm. To stand beneath the night sky and glimpse the faint smear of the Milky Way is to witness a cross-section of that eternal spiral, frozen in light years of perspective. The stars we see form only a small fraction of the structure. Most of it lies beyond sight, shrouded in gas, dust and distance. Yet even through that obscurity, the spiral's influence pervades everything. It shapes the orbits of stars, channels the flow of interstellar gas, and dictates the pace of star formation. Its arms are the pathways of creation, where matter condenses into light, while the spaces between them serve as resting grounds, where older stars drift in quieter orbits. This interplay between arm and void, motion and stillness, gives the galaxy its living rhythm. The spiral form is one of nature's oldest and most universal designs. It appears in the shells of sea snails, in the curling of hurricanes, in the pattern of galaxies billions of light-years away. It is the geometry of growth, the architecture of energy unfolding. The Milky Way, in following this pattern, participates in a cosmic language that spans from the microscopic to the infinite. The same mathematical ratios that define the swirl of a nautilus shell also govern the distribution of our galaxy's stars, a reminder that the universe operates through repeating harmonies, that form and motion are one. The Milky Way's spiral is not perfect. It is warped, asymmetric, constantly shifting under the influence of passing companions and internal resonances. Yet that imperfection is part of its vitality. The warp in the outer disk, caused by interactions with smaller galaxies, gives the Milky Way a distinctive three-dimensional grace, like a ribbon twisting in wind. The unevenness of its arms, some bright and sharp, others diffuse and fading, reveals its long history of encounters and evolution. Perfection, in the cosmic sense, is not symmetry, but persistence. The spiral endures because it adapts, because it flows. Over billions of years, as the galaxy merges, warps and reforms, the spiral reappears, sometimes tighter, sometimes looser, but always recognizable. Even when the Milky Way eventually collides with Andromeda, the spiral's essence will survive. For a time, the two galaxies will twist together in a magnificent cosmic whirlpool, their arms stretching into luminous filaments that trace the invisible currents of gravity. And though the final merged system may lose the distinct shape of a spiral, its stars will still follow paths carved by that ancient motion. The spiral in this sense is immortal, not as a static form, but as a principle of order woven into the fabric of the universe. To understand the eternal spiral is to grasp that nothing in the cosmos is still. All is motion, all is transformation. The spiral embodies that truth, showing how chaos gives rise to structure, and how structure dissolves back into chaos without ever truly ending. It is the universe's signature of continuity, the shape of galaxies, storms, DNA, and time itself. The Milky Way's spiral arms are its heartbeat, the visible expression of an invisible rhythm that pulses through space and through us. Every revolution of the galaxy, every new star that ignites, every dying ember that returns its light to the void, is part of this great pattern. It reminds us that beauty in the universe is not carved in permanence but written in motion. The eternal spiral is both the galaxy's body and its soul, a symbol of unending creation, forever renewing itself as it turns. In that sense, the Milky Way is not merely a collection of stars, it is a cosmic poem, a living vortex of light and gravity whose verses are written in motion and whose refrain is eternity itself.